Good afternoon. So today it gives me great pleasure to introduce today's speaker. He and I worked together for a number of years at Fermilab, and it's whoever decided to invite him. It's really a great pleasure for me to be here. He did his undergraduate studies at the Institute of Technology in Eindhoven. He got his doctorate from the University of Amsterdam in 1986 or so. He was then a postdoc at the State University of New York in Stony Brook before he was lured to Fermilab by a Wilson Fellowship. He stayed at Fermilab for several years, and in 2010 moved to Argonne National Lab. During his career, in his doctorate, he worked on tau meson production and decay, and in p-bar-p physics on the D0 experiment, maybe most of you know, but maybe not, the kind of rite of passage for a hadron collider experiment is to do a good job of measuring the mass of the W boson, trying to do precision physics in a very high energy collider. And Marcel was instrumental in the first measurement that D0 made of that quantity in the early 90s. He then took on another thankless task as one of the leaders of the silicon detector project for the upgrade of D0. That was a device with 800,000 channels and nearly as many problems on the way to completion. But completion it was achieved, and in fact it ran right through to the end of the collider running at Fermilab. So some rather impressive achievements in his career, but now he's paying for it. He's a member of the Bell II Program Advisory Committee. He's a member of the Large Hadron Collider Committee at CERN. He, for our benefit, is a member of the Electron Ion Collider Detector Advisory Committee at Brookhaven. And then to complete all this, he's got the pleasure of being a member of the Particle Physics Project Prioritization Panel, which is trying to give a shape to particle physics in this country this year. So it's with great pleasure. Please join me in welcoming Marcel Demarteau.
All right, well, thank you, Ron, for this nice introduction. I don't think that measuring the W mass is still a rite of passage for hadron collider experiments, because I don't think, Atlas and CMS will be able to accomplish that measurement anytime soon. Anyhow, so again, thank you very much for having me here. It's a great pleasure to be here. And this talk is maybe not going to be as much physics as you may want, but maybe more of the direction in which physics is going, and in particular particle physics. So what I would like to talk about is the tools, the techniques, and technologies of high-energy physics and the connections of these technologies. And to give you a little bit of the background, this actually came about very tangentially to the process that the particle physics community is going through at the moment with its prioritization, in the sense that Jim Segrist, who is director of the Office of High Energy Physics in the Office of Science, would like to understand better, what the relation is of high energy physics to other science disciplines and society in general, and that's how this came about. And again, so this is somewhere, where it is still work in progress to understand these connections and the relationships. So if you have any feedback on that later, that would also be greatly appreciated. So you all know what particle physics does. Particle physics had its humble beginnings in a handheld cyclotron that was developed by Ernest Lawrence, and then it developed these very massive machines that have accomplished a lot. So the last machine that we had that had the energy frontier was the Tevatron at Fermilab, which has now been superseded by the LHC at CERN. Now, what particle physics does is it just studies the fundamental interactions of nature. It studies the fundamental constituents of nature and their interactions, which is nicely captured in this graphic. Now, the way particle physics goes at that is by building detectors, as anyone does. And the detectors that particle physics has built are really, I think, triumphs in instrumentation. The size of these experiments and the complexity of these experiments are really unique, I think, in the field of science. So here's a picture of the ATLAS experiment. Just for the scale, this is a person. And the other experiment is, the CMS experiment. And it really just captures the imagination. It fascinates us, but it also captures the imagination of the public, because it actually does make the front cover of, popular magazines like Newsweek. Even though it does capture the imagination of the public, you also know, and we all know that, journalists often get it wrong. And just as a side note, even though this is here on the cover of Newsweek, there are two mistakes on the cover. The first one is, it says, this is the picture of CMS, and it says that CMS is the biggest experiment. Actually, it's not the biggest. ATLAS is the biggest. It's the heavier one of the two, but ATLAS is the bigger one. And the other one, which is, I think, a big mistake, it says it's European, and it's not European, because the US has contributed more than 30% to both of these experiments, and has contributed significantly in actually the machine. But with these experiments, we tried to get at the science, and for the last couple of years, the field has also made, I think, enormous strides in getting at the science. I mean, 2 years ago, both the ATLAS and CMS experiments discovered the Higgs boson, and this is a picture of the Higgs decaying into 2 gammas. Then, the experiment at Daya Bay in China has a reactor neutrino experiment, has measured one of the last remaining parameters in the PM&S matrix for the neutrino oscillations, and measured the angle sine squared theta 1,3, and measured it to be rather small. And then, as you all read, I'm sure, is that 2 weeks ago, the BICEP collaboration had the first evidence of actually inflation and gravitational waves by looking at the cosmic microwave background radiation. And they measured this parameter R. So here is the power spectrum as function of angular momentum. And this blip here is the indication that R, which is the ratio of the tensor to scalar ratio, so really, the effect of gravitational waves is actually much larger than people had expected. So the question then is, to just put this in perspective, particle physics, of course, has not done this alone. It has relied tremendously on other science disciplines, but at the same time, particle physics has had a broad impact for other sciences and for society as a whole. So the question is, what are the key connections and the synergies between these tools, techniques, and technologies developed for particle physics and other disciplines? So what I would like to do is to look at these impacts, and go over them one by one. So what I would like to do is first look at the detector technology, then go into computing, accelerators, and then facilities. And then I will conclude with what I view as some outstanding issues, and then especially what the opportunities are for all of us. So first, detector technologies. So this is a major area of connection of particle physics that has reached, I think, all the way from medical industry to actually imaging detectors. So one technology that I would like to highlight is the silicon technology. The silicon technology that high-energy physics started and brought it to such an unprecedented scale that we see now realized in these LHC experiments actually had its beginnings in industry. It is because industry developed, the lithography and the integrated circuits. Is that what, particle physics capitalized on and started to make these silicon detectors. So again, it had very humble beginnings. Here's a picture of 1987 of an experiment at Fermilab where the area of silicon here is about 25 square centimeters. That developed all the way to, current experiments where the area of silicon is more than 200 square meters. In parallel with that, what was developed is application-specific integrated circuits. So these are integrated circuits that read out these devices. Now, believe it or not, but this technology that lies at the basis of this has been applied in neurobiology. Because, so it was, in some sense, the crossing of the path of a particle physicist and a biologist to try to understand the problem that the biologist faced is he said, he wanted to measure the nerve pulses at the end of a retina. And what they developed is exactly the same methodology that we use in silicon detectors because you have a pad array of electrodes, you wire bond it, and you read it out with an application-specific integrated circuit. So you use exactly the same methodologies and the same techniques and the same readout circuitry that was developed for particle physics to study the eye. And what they discovered actually that there's a new functional time of the retinal output that was not known before they did this. The other area where particle physics has had a tremendous input and still has a tremendous impact is medical imaging. So here in proton-computed tomography, what you do is it's much better than tomography with gamma scattering. It's where you use protons. So you measure the direction of protons very precisely before the object, very precisely after the object. So you measure the scattering, and you measure the energy loss of the proton in a calorimeter behind it. So this proton-computed tomography is being developed at the University of Santa Cruz, and what they use is, again, silicon detectors, silicon strip detectors, to measure the trajectory of particles, and then a calorimeter to measure the energy loss. And the readout of this is exactly the same readout that were used for the glass Fermi telescope that is up in space. The main difference between this application and the application in space is that if you want to do proton-computed tomography, you have to read these out. You want to measure, 1 million protons per second to actually be able to image, a person very rapidly. Now, this technology, has migrated to nuclear physics. Even here at JLab, there is the JLab Class 12 experiment where part of the ASICs that were developed that are being used to read this out were developed at Fermilab and also at Phoenix. The SVT at Phoenix uses the readout that was developed at Fermilab for run 2. And some of the assemblies actually occurred also at Fermilab. Now, one way to go beyond where we currently are, to increase the power of where we currently are, is to go in a different direction with silicon technology, and that is using what they call monolithic active pixel sensors. So in a monolithic active pixel sensor, what you do is you have a sensing medium, which is still silicon, but in the sensing medium, right on top, you also have the first stage of your front-end electronics. So you can do the processing, and you can put the logic and the intelligence right there where you do the measurement. Now, this technology was conceived by the particle physics community, but at the moment, it's the nuclear physics community, it's you guys, who are really running with it. So the first application of this technology is in the STAR heavy flavor tracker. where they have a couple of layers of silicon detectors. And the further development of this technology could, again, really be very beneficial to particle physics. Again, to indicate you that the nuclear physics community is really pushing this technology very, very hard, here is a picture of the ALICE inner tracker system, which is looking at the construction of a 7-layer tracker that will use 25 gigapixels. It's the largest pixel detector that has ever been built. Similarly, for the experiment at GSI, where again the first 4 layers are going to be built with this technology, with the added requirement that it also has to be radiation hard, which is really something that particle physics community would be very interested in. Now, the pixel technology, the silicon pixel technology, has also spun off into the X-ray community. So while the CMS pixel detector was being developed, and here's a picture of the CMS pixel detector, they realized actually that you could use the same technology to also measure X-rays. And the company was spun off called Detector that has developed, these X-ray detectors, which are now the workhorses at almost any light source. Now, taking this even one step further, in Europe at the XFEL, there are a couple of X-ray detector projects that are being developed. The 3 are shown here. One is a hybrid pixel detector, the other one is a large pixel array, and the other one uses another technology, DepFed, that came out of the particle physics community. But again, these are all built as a collaboration between the particle physics community and the high energy physics community to enable their science. Now, integral to all of this technology is the readout. So as I mentioned already, application-specific integrated circuits were fully pushed by the particle physics community. And this is, I think, a rather interesting example of the path that these technologies have followed. So in around 1999, the the nuclear physics community actually needed a readout for the ALICE experiment at the LHC. And they developed a chip that was used for the pixel detector at ALICE. Then the project essentially stopped because there were no follow-on projects. But while working on the project for ALICE, they realized that this was a damn good chip to also use for X-rays. So out of this came the development of the MEDIPIX and the TimePIX development that is now being used to make these X-ray images. Now, it turns out that in these 10 years of development, and they really have pushed this development, now they have a chip, the TimePIX 3, which almost meets all specifications for the upgrade of the LHCb detector. So it is not, it was, the way I view this is, enlightened management that let this project go on and maybe have a little detour from its path has fully paid back, the investment that was made. And to show you here a picture, this is a picture that was taken by the TimePIX, the MEDIPIX 3 chip, which shows the contrast that you achieve with this device. And these are 4 keV, gammas. And the only way you can get this, if you really have single photon efficiency and very, very low noise readout. If you compare this to the X-ray you get from your dentist, the difference is striking. I find it striking. Let me just change track here a little bit, and that is crystal development. So, we knew that BGO, which is this crystal, bismuth germanium oxide, existed in the 70s. But the L3 experiment at LEP at CERN decided to actually at one point build an electromagnetic calorimeter using these crystals because it had the best energy resolution. And this is, again, something that is unique to particle physics, and that is the scale of these devices. So L3 needed about 11,000 of these crystals, and at the time that they wanted it, they could only grow a crystal one at a time. But they contacted, this Shanghai Institute of Ceramics, and they developed, in conjunction with this company, a method where they could build 36 crystals in one shot. And that simply was the breakthrough to make this technology available to the medical imaging industry, because then it suddenly became cost effective. So this opened the medical market, and 1,500 PET scanners have been built by GE Healthcare, using crystals grown by this method by the Shanghai Institute of Technology. Now, another example is the development of LISO crystals. So during the last phase of the LHC, when CMS was building its electromagnetic calorimeter, they decided to use lead tungstate. One requirement for the LHC experiments is always that everything has to be radiation hard. So when they were looking at the radiation hardness of lead tungstate, what they discovered is a way to make lead tungstate radiation hard. That is through special annealing and yttrium doping. Now at that time, LSO was already discovered by Schlumberger, but somebody put these two together. So somebody, and he gives the particle physics community full credit for that. He says, that because of the yttrium doping, he, invented LISO. LISO stands for lutetium yttrium, silicon oxide. So that is the crystal that is now being used most within PET scanners in the medical industry. So here again, and now, in turn, the particle physics community can use these crystals for their next generation of experiments, because the mu2e experiment at Fermilab would like to use LISO crystals for their calorimetry. Now, this one I put in because it is the basis of the result from 2 weeks to look at gravitational waves. Because these gravitational waves have been detected with transition edge sensors. Transition edge sensors have been fully developed by the particle physics community. There's just no doubt about it. And what is a transition edge sensor? It's a little calorimeter also. So what you do is you have an absorber, and when a photon comes in, the temperature of this absorber increases slightly. And this absorber is a superconducting material. So what you do is you engineer this superconducting material to be right at the transition between superconducting and normal conducting, so that you're sensitive to the slightest change in temperature. So the slightest change in temperature gives you an increase in resistance, changes the current because it's voltage biased, and you read that out with a squid. And these devices are now, because they are phenomenally sensitive, they're being used in many different applications. Here I show two applications. The top plot shows, this is the energy in keV, and these are the spectra. So this is what you would measure with sodium iodine all the way up to a transition edge sensor. And you can see that with a transition edge sensor, you can distinguish all these individual peaks. Similarly for a biological application, because of their sensitivity. And they're also being used to really look at fundamental quantum mechanical processes, like looking at the Rosen-Einstein-Podolsky paradox. Now, some detectors that we use are, large area and relatively cheap, like these resistive plate chambers. So in resistive plate chambers, you have two plates filled with a gas, particle goes through, ionize it, you have an avalanche, and you read it up. Now, because again, the scale of the particle physics experiments are so large, you need these in large format, make them cheap, and how else can you use them? Well, the environmentalists have tried to use these to actually look at imaging, for example, an imaging of a dormant volcano in France, where they study, the interior of the volcano. So that was all I wanted to say about detector technologies. And now I would like to move to computing, what particle physics has done in the area of computing. So first is particle physics is known for big data, but big data means something different these days than it did 10 years ago. So, Eric Schmidt, who is the CEO of Google, says that from the dawn of civilization until 2003, all the data that humankind generated, now we produce every 2 days, which is really true. But, particle physics is still recognized as the field that really pushes big data. So, as you all know, the World Wide Web was invented at CERN, and that was a response to the need, for scientific collaboration. The grid is a response to the need for increased data analysis power of all the data that comes out of these LHC experiments. So what you need for grid computing is really reliable high bandwidth networks and then access to these high compute power systems. So again, this shows you the problem that the LHC faced. Here is the event size in bytes versus the rate of these events. And this is where the LHC experiments live. And you can see that, they are really, really pushing the rate and the size of these events. So then what the particle physics community did is they worked with the Energy Science Network, ESNet, to really develop a system that met the needs of particle physics. So this was really an interaction, a collaboration between the two, between the computing science group and particle physics to develop this. And based on that, the LHC also developed the worldwide LHC computing grid, and it was built on two backbones, the European Science and Grid Infrastructure and the Open Science Grid in the United States. And again, the tools were all developed and for grid computing, and now grid computing is not limited anymore to particle physics, but there's a whole range of science disciplines that now, for them, it is the norm to carry out their analyses. Now, I would like to give you a quiz. And the reason why I give a quiz is I'll come back to that later. This is a quiz on big data. And this is from Wired magazine from last year. The size of the circle represents the size of the data volume. The question to you is, which circle represents the LHC data? I'll give you the answer. This is the LHC data. You can see that Facebook, which didn't exist, and this is important, Facebook, which didn't exist when the LHC was proposed, which didn't exist, 5-6 years ago, now just overwhelms everything with all the pictures of the dogs that get uploaded every day, on Facebook. Another thing that I think high energy physics can take credit for is the development of scientific Linux. It was actually developed at Fermilab and then later in collaboration of Fermilab and CERN. And now, it has a relatively small user community, but it does run on the International Space Station. And it is listed as one of the 20 innovations in the Chicago area that happened. By the way, some of the other inventions on that in Chicago are listed here. So it's interesting to see that it competes with the invention of the vacuum cleaner, for example. Then another thing, and this is where nuclear physics and particle physics have done together, I think, had a lot of impact. And that is the development of supercomputing through lattice QCD. So lattice QCD, at one point the theorists needed a way to tackle lattice QCD. And in the beginning, the theorists, tried to come up with a way to actually carry out these calculations. This, by the way, was Ken Wilson who started all this. And then in the 80s, they actually began developing machines that were really aimed at the performance of lattice QCD calculations. So the initial effort there was really an effort, but again, as I said, between the nuclear physics community and the particle physics community at Columbia, and that then grew, to the development of the first set of supercomputers, the Blue Gene supercomputers, developed by IBM. A few of the key people who were involved in this project from the start actually moved to IBM to develop supercomputing. And then, again, high-performance computing these days is being used in a broad range of applications, from studying climate change to looking at thermonuclear fusion. Another thing that many people may not be aware of is JON4. I don't know how well it is used within the nuclear physics community, but JON is a simulation package that has a very interesting set of tools to define the geometry and look for tracking. So you can define any medium that a particle goes through and look at the interactions that happen. And this, even though it was fully developed to simulate what comes out of a particle physics collision, has found enormous applications. These are all the projects in space where JON4 has been used, and it's pretty significant. They're also being used for other, planetary missions. They're even being used now to study for DNA models. They look again for medical imaging, and even single event upsets are being studied with JON. And another thing is that even Boeing uses it. Boeing is using it to look at the radiation dose for their flight crews, and actually there is a paper on it, and I even before I started to study myself, I was not aware of this paper, where it is interesting to see, that particle physics is actually trying to design an Airbus and look at what can be done in designing an Airbus to minimize the radiation effects on all of us when we fly and the crew that actually, the airline crew. Okay, then we come to accelerators. So accelerators, as you all know, is the workhorse for particle physics. At the moment, they are being used in a broad range of applications. So they're used to look at material science. Many discoveries are being driven by particle accelerators. And here again is a list of topics where accelerators are being used. So anyone, for example, who has an artificial hip or something, your hip has been treated with a particle accelerator because there's nitrogen ion implantation of the titanium here to make this a much better joint. Now, of course, there's also ion therapy, where again there's a huge overlap with nuclear physics. So these are the Bragg curves, the energy loss as function of the depth, in this case for water. And you see that photons or X-rays have a rather broad spectrum of where they lose their energy. But we all know that protons, and especially carbon ions, have a very sharp peak in where they deposit their energy. So for specific tumors, ion therapy is really the most ideal therapy to treat certain forms of cancer. So this is a picture of the Heidelberg Ion Therapy Center in Heidelberg. And as you can see, it is very similar to, a particle physics or a nuclear physics facility, but it is being used to treat patients. Then we have superconducting RF, where actually nuclear physics is a major leader in that. So it's a major thrust for the next generation of particle accelerators. And this SRF is really driven by a collaboration between nuclear physics, particle physics, material science and chemistry. And again, it is exactly, I think, this type of collaboration with other science disciplines that really will drive this technology and this further, because we need the interaction with the material scientists to understand, where a cavity, for example, breaks down, or why you cannot reach the gradients that you actually want to achieve. Now, accelerators are used in industry almost everywhere, from disinfection of water to ion implantation for silicon devices to heat shrink films. Now, you all know also that we are starting to reach a limit with the scalability of accelerators. They're just becoming quite unaffordable. So one way to break that barrier is maybe through laser-driven acceleration. But, and this may really be required to enable us to make our next generation of particle colliders. But what this relies on is really advances in areas of science that are beyond particle physics. Because here you really need lasers, for example, that have kilowatt average power with terawatt or petawatt peak powers, with a large efficiency and with a high rep rate. So particle physics will become more and more dependent on these other technologies. The last topic is a few words about facilities. So we have HEP-operated facilities, so accelerator-based particle facilities. But one very nice example, for example, is the test beam at CERN was used for a cloud experiment. And the cloud experiment stands for cosmics leaving outdoor droplets. That is an experiment that is looking at the formation of aerosols and the formation of clouds using aerosol particles in the sky. So it's really an atmospheric study where they use particle physics facilities to actually get at that science. And the reason why particle physics can do that is they can provide them with particular beams that simulate cosmics, and they can provide the environments that they need. For example, the very ultra-high vacuum environments that we have for the beams, and in this particular case, in this huge vessel. One thing that is very appealing to me is the sharing of facilities already between the different disciplines. So here we have a particle physics experiment, the heavy photon experiment, that is, I think, a particle physics experiment, but it's taking place here in Hobby. At the same time, there is the experiment Sequest, which really looks at the composition of the C inside a proton, which is, falls under nuclear physics, which is actually taking place at Fermilab. And I really believe that we should have much more of that. Then we also have built facilities that are really built by particle physics. So we built, for example, these sky surveys. Fermilab built the dark energy camera, which is an array of about 60 or so CCDs to carry out these sky surveys to look at dark energies. It's built by high energy physics, but it really benefits a much broader community. And then, we have these huge infrastructures like SLAC and, Petra at DAISY that are now being used as light sources where, basic energy scientists can just come in and use their facilities, these large facilities, the large investments in infrastructure for their physics. Then we have detectors that can be used for geophysics. I mean, some people say that we understand the inner core of the sun better than we understand the inner core of the planet that we live on. But one way to study actually the inner core of the Earth is to look at geoneutrinos. So, you know, the neutrinos coming off of the interactions in the Earth, and the experiments that we have, the large neutrino experiments that we can have, could actually be very beneficial. It could serve, you know, the geophysical community rather than just our own community. And then we could go a step forward. I mean, if we are going into the direction of muons, for example, at Fermilab, you know, they're trying to create muon beams. Maybe one could think of creating a facility for stopped muon beams. At the moment, the US does not have a stopped muon beam facility anymore. We had one at Los Alamos, it was shut down. And now to do any one of those studies, you know, people have to go overseas. And muon spin resonance is a very sensitive probe, especially for material science. So this is being used to look especially at superconductors, at magnetic phase diagrams, and that facility could be provided by, for example, particle physics for, you know, the benefit of a broader society. So I would like to conclude then here. So I think what I try to do is to show that there is a web of connections of particle physics to other science disciplines and to society, and that web is rather broad. And none of the two tools that were developed by particle physics had any of those applications in mind. It was just purely curiosity-driven, basic science. But it found its way into broader society. And often, the path these inventions and these developments have followed was rather serendipitous. It's just by chance. But the value of these connections, I believe, is rather substantial. But the question is, what opportunities can be identified for expanding and strengthening these connections in a structured way that helps all of us, that helps, you know, advance science, helps advance technology, and helps, you know, benefits for society. So the reason why I showed you this quiz about with Facebook is that quite a while back, you know, especially for particle physics, the developments that were being done by particle physics were in sync with the developments in industry. We actually pushed industries in many aspects. For example, with the silicon technology, with the development of the integrated circuits, you know, the requirement of particle physics to make integrated circuits radiation hard gave industry new ideas. They came up with ways to, you know, enclose transistors in an IC. But, and the other advantage of particle physics is, you know, that particle physics is required to bring these technologies to scale and make them work. Now, because of a multitude of reasons, that is not the case anymore. Projects within particle physics take a very long time, and there are technologies in other areas of science that are just have overcome us. As I said, when the LHC was written down on a piece of paper, Google didn't exist. Facebook didn't exist. And now, their demands on getting access to data and transporting data over this infrastructure is much larger, much higher than what we need. So we have to take a new look at that. So what are the opportunities? I believe that there are plenty of opportunities for, you know, groups to work together, to form collaborative efforts. So in detector technology, I really think that the field has to look at partnering with other fields, like materials science. I do think that, you know, we could work with the light sources here in the country to develop better detectors for the light sources. And I think, we should partner up in a more coherent and a more collaborative way, with nuclear physics. The same for computing and data management. There are a lot of things that we can do, especially in the area of high-performance computing, where, we could really benefit. Then in accelerators, I think that has been documented quite well in these 4 reports that you can find on the web. But one thing that I would like to mention is, and I'm a bit reluctant to use this word, but it's the word stovepiping. We have to, break these barriers between the various science disciplines. At this moment in time, it is very difficult for somebody to work for, a couple of months in a completely unrelated field, unless you have a budget code. And often that is a limitation. And that I think, has to change. And similarly for facilities, I think, we should explore really if joint construction of facilities that we have demonstrated already that they are very good and can cater to a very broad community, how we can expand that. So in conclude, and I would like to say that the time has come really to articulate, in a better way, these overarching opportunities for us to work together. And I think, 2 ways that I would like to see is really the formulation of joint strategies to address technological challenges, but joint strategies beyond one scientific discipline. And so really the creation of these multidisciplinary, multi-institutional research programs. And I think, together we are stronger. Thank you.
Questions? Well,
I can't help but ask this question since I had my hip replaced last December. So how does the ion implantation help the titanium become have better affinity to bone structure?
I'm afraid that I cannot answer that question, but there are 2 issues there as far as I understand. One is the wear, of the titanium surface, and the other one is actually to have less friction between the 2 surfaces. Why nitrogen, in titanium gives you this result? I am sorry, I don't know the answer to that.
Jim Boyce?
Can you comment on the recent article from the New York Times about private funding for research, the billionaires funding big research like this, and whether that is good or useful or not?
That is a very interesting question. I personally believe, there are 2 aspects again to this. To have private industry fund research, I think is a good thing. What I do not really like is then that you're beholden to, the private donor. I really think that, and this is a question for us as a nation, I really think that it is the responsibility of the government really to value, to decide how much value they want to put in the development of new technologies, in the development of new instrumentations, be it basic science or applied science. In that sense, I think that the Europeans are doing a much better job at that. If you look at, in Germany, for example, you have these Fraunhofer institutes. These Fraunhofer institutes get a chunk of their money from the government. And what they then do is they team with industries and they team with universities to come up with new ideas, new technologies that advance, whatever problem they are addressing, be it, again, applied science or fundamental science or very pragmatic. And, I think that here in the US, we are really desperately lacking some kind of initiative like that. The other thing that I want to mention is if you look at the European community, they have these 4 to 5 year, frameworks, and the next one for the next 5 years is called Horizon 2020, and that is run by the European Commission, where Europe decides, what the emphasis should be in terms of investments in, basic research, and in this particular case, very applied research. And they are putting, you can look it up, you can Google it, they are putting $200 billion in as an investment, as Europe, as an investment in the development of infrastructure that will really move Europe ahead.
So can I push back a little bit there? So I was on a review in Saclay in January, and one of the complaints from the scientists in IRFU was that they, as a result of the initiatives everywhere and the inhomogeneity of the funding scenarios, that they were spending a very significant part of their time writing grants, grant proposals, and they miss the if you like, the monolithic funding of a laboratory in which then the director shared it out without any administration, if you wish.
Fully agree with you. Even though I mentioned the number $200 billion, what actually trickles down to the various institutions is very small. I mean, CERN is looking at, something like $25 million, 25 million euros that they want to get out of that. And the overhead in writing grant proposals, being reviewed, is bordering, being ridiculous. I agree with you.
And the other thing I would say in support, with respect to Jim's point, I would argue that the IBM Watson Center and other, these were, if you like, private investments, right? And they were a major driving force of U.S. science for many years. I mean, you wouldn't have the cosmic microwave background to talk about without that.
I mean, I agree. There's a lot of advantage to that. But I think it has to be a balance. I think you should not just rely on private funding.
You talked about miniaturization of electronics and radiation hardening of electronics, and you didn't mention NASA, and I would, in my mind, have felt that NASA would have been one of the leading agencies working on those two issues. Comments?
To the best of my knowledge, the radiation requirements of integrated electronics at the LHC are much more stringent than anything that you have out there in space. So the enclosed structures that were developed, by the semiconductor industry, but with a large, feedback and large input from the particle physics community, really has benefited NASA too.
Where did the DMIL specs come into that? So I mean, when we started the LHC designs, then the radiation hardness was dominated by DMIL stuff, right?
Yes, that's correct. But you also know that then Jeff Hall really, so DMIL was abandoned. Yeah, so we went to quarter micron technology, and there the designs were modified and adapted to really make sure that quarter micron technology was radiation hard for the LHC experiment, and DMIL was abandoned.
Yeah.
You mentioned the Alice Giga channel tracker. Just wondering what will be the cost for that?
the Europe only gives you core cost. And the core cost, which is just, materials, for the ALICE tracker is, if I'm not mistaken, about 15 million Swiss francs. Again, this is where I think these new technologies are very beneficial, because the process that they use is a regular CMOS process. So it is relatively cheap. If you had to do this with a dedicated process going through Hamamatsu, it would become pretty quickly unaffordable. And the number that I quoted was for the overall project, not just for the silicon, not just for the sensors.
Other questions? If not, let's thank Marcel again.